Welcome back. Today, we're diving right into a brand new explainer, and honestly, we are about to play the role of cyber detectives. We're going to look at exactly how neural networks can literally be forced to cough up their deepest, most internal secrets. We're talking about a system that totally shatters the way we think about the so-called AI black box.
First up, we need to talk about the neural privacy illusion. You know the drill, right? It's that widespread belief that the second your prompt enters an AI, it gets pureed into this unreadable, lossy soup of numbers. For the longest time, everyone kind of just assumed that hitting send irreversibly scrambled the text. But what if that's completely backwards? What if your original text is perfectly intact, just, hiding in plain sight?
There's a brilliant quote from the source material that says, "The machine's silence is an admission," and that really hits the nail on the head. We actually have the fingerprints. Engineers call them hidden states. And we're going to use a highly specific mathematical hammer to smash open that black box and extract the absolute truth straight from the machine itself.
Section 1. The neural privacy illusion. Let's officially shatter this myth.
Right, so for ages, the consensus was that the crazy, complex math inside transformers inherently destroyed the input data. Traditional methods for figuring out what went in relied on approximate, lossy statistical guessing, basically looking at the generated output text and trying to reverse engineer the prompt. But the new reality? It's a precise, structurally lossless forensic reconstruction. We're no longer relying on educated guesses, folks. We are talking about absolute, ironclad mathematical proof.
Moving on to Section 2, the math of injectivity.
Okay, so injectivity. It's a fancy math term, but it basically just means that every distinct input has a perfectly distinct output. Think of it like a totally unique key for every single lock. The researchers prove that standard transformers are almost surely injective, and the implication there is huge. It means your data isn't lost in the wash. Those internal activations? They are perfectly preserved. They are quite literally your prompt, just wearing a really clever disguise.
Section 3. SIP-IT, the technical hammer. Now, how do we actually exploit this mathematical reality? We use a specialized auditing engine designed to force uncooperative models to, confess. It's called SIP-IT, which stands for Sequential Inverse Prompt via Iterative Updates. Here's the magic. Because a hidden state only really depends on what came immediately before it, SIP-IT doesn't need to guess the whole sentence at once. Nope. It just walks through the sequence, interrogating the machine step by step, position by position.
Section 4. Lisp Logic Core and Token Recovery. All right, let's look under the hood at the actual Lisp logic driving this extraction, because this is where it gets really cool. It relies on a dynamic duo of functions. First up is a function called SIP-IT extract. This takes a list of observed hidden states and recursively reconstructs the entire sequence. For every single state, it calls its partner in crime SIP-IT position. Now, SIP-IT position inverts a single token position using a candidate policy. It looks for a unique match between the predicted state and the observed state. If it finds the true token, boom. It appends it to our recovered prefix, and SIP-IT extract loops to the next state. If not, it just updates the policy and tries again. To put that formal logic into plain English, the algorithm is basically checking a candidate token against the observed hidden state to see if it falls within this incredibly tiny margin of error, known as an epsilon ball tolerance. We're talking something microscopic, like 1e-6. If it falls in that zone, it's a unique match. The system locks in that true token, adds it to the growing sentence, and seamlessly loops to the next position. Absolutely no statistical guessing involved. It is pure forensic proof.
On to Section 5. Linear time and gradients.
Now you might be sitting there wondering, wait, with a massive AI vocabulary, wouldn't checking every single token take like 1,000,000 years of brute force computing? And normally, yeah, it would. But the secret sauce here is a gradient-based policy. Instead of painfully checking a dictionary word by word, the system calculates the distance gradient. It instantly updates a continuous proxy embedding and ranks the entire vocabulary, which means it often points exactly to the true hidden token in a single elegant pass.
And because of this engineered precision, SIP-IT recovers the exact input sequences from those hidden activations with absolute 100% token-level accuracy. And it does it in provable linear time. Honestly, that's mind-blowing. It's not an approximation, it's not a best guess, it is a perfect one-to-one extraction of the user's original text.
Which brings us to Section 6, the end of free privacy.
We really have to confront the massive systemic implications this has for data security. As the research points out, there is simply no free privacy once a prompt enters the transformer circuit.
period. If a corporate API is sending you hidden states, they are functionally sending you the raw user prompt itself. It acts as a tamper-evident audit spine. The machine literally cannot lie internally because the shimmer of its activations is a permanent, irreversible record.
So I want to leave you all with a rather provocative thought. As we strip away the layers of this black box, we really have to ask ourselves, who actually owns the machine's thoughts? And what does true privacy even look like in an age of perfect forensic reconstruction? If every single internal activation can be flawlessly inverted back into plain English, well, the boundary between human intent and machine execution has completely dissolved. Thanks for joining me on this explainer, and stay curious.